So now let's say you're integrating cosine to the fourth of 5 theta d theta. So the rule of thumb that I've given you up to this point is look for an odd exponent. Look for a sine or cosine to an odd power, split off one power from that expression, and form a differential du based on that one power that you split off. That works well when you have an odd exponent. But in this case, I've given just one trig function. It's to an even power. Notice that if you try saying, okay, well, if I'm stuck with cosine, say I break off the power of cosine. So if I write this, I'm going to switch, this black marker needs to retire. If I write this as cosine cubed times cosine to the first, 5 theta, d theta. And if I say, okay, that's going to be my du, then u would be sine of 5 theta. We'd have to have a multiple of 5. Okay, but let's not worry about that. We could resolve that. So if u is sine of 5 theta, then that means I need to write whatever's left here completely in terms of sine. When you have an odd exponent, you actually can't do that. So cosine squared, we could certainly turn into 1 minus sine squared. That'd be great. But then you're going to have this extra cosine of 5 theta hanging off the end. Odd exponents can't be written completely in terms of the other. So if you've got a sine or cosine to an odd power, you're not going to be able to write that completely in terms of the other trig function. You can't translate it when it's odd powers. I mean, if we're using this trig identity, equals 1 minus sine squared. So it's only going to work when you have a power of cosine squared, which any power of cosine squared is going to be an even power because you'd multiply the exponents here. It's going to be to the 2n power. So when you have something that's not, that form, so an odd exponent, then it's kind of a dead end. You can't translate that to sine. So forget writing it completely in terms of sine. That substitution's not going to work. So when you find yourself in this situation where you have an integral involving just an even power, you take this advice, which I was purposely trying to block. So for integrals of the form some power of sine of x times some power of cosine of x, where your powers are, the only powers you have are even, you use what's called a power reduction formula, which I haven't written down yet because I wanted to talk these through with you. So the power reduction formulas are really just, it's a version of the double angle formula for cosine, rebranded in Calculus 2 as power reduction formula, but it's the same equation. So if you remember from your trigonometry days, whether that was in pre-cal or high school or trig course, maybe you remember the double angle formula for cosine, which says cosine of 2 theta is equal to, so it's actually got a few different versions, but the way I think of it, the primary version is cosine squared theta minus sine squared theta is equal to cosine of 2 theta. Here, let me write this down in case it jogs your memory. Double angle formula. Notice that if you substitute, say a cosine squared we know now is 1 minus sine squared. So if you substitute 1 minus sine squared here, you'll have 1 minus sine squared minus sine squared. So 1 minus 2 sine squared theta. Similarly, if we substituted a 1 minus cosine squared here, so you have cosine squared minus parentheses 1 minus cosine squared, distribute the negative, you'll end up with positive 2 cosine squared theta minus 1. Now, if you find yourself, like in this scenario, stuck with just an even power of cosine, here's what you can do. So what if we just take this version of the double angle formula for cosine? So cosine of 2 theta is equal to 2 cosine squared theta minus 1. So say I take that equation and I add 1 to both sides. So 1 plus cosine of 2 theta is equal to 2 times cosine squared. And then divide both sides by 2. Then this equation right here is what we know as the power reduction formula for cosine. So when you have an even power of cosine, cosine squared theta here is equal to this, which I'm going to write as 1/2 instead of putting it over 2, I'm going to write it as 1/2 times 1 plus cosine of 2 theta. So you don't have to know, how to derive the power reduction formulas, but I just feel like it's a lot easier to use this stuff. It's certainly easier to remember if you have some sense of where it came from. If we did the same thing for sine, which I don't think I'm going to write all the details in this video, but if you take this version of the equation, so cosine of 2 theta equals 1 minus 2 sine squared theta, and solve that equation for sine squared theta, you'll end up with 1/2 1 minus cosine of 2 theta if you work out the details on that. And so that's your power reduction formula for sine. Notice, okay, so remember it's coming from the double angle formula. So notice when you apply the power reduction formula, the angle gets doubled here. So you go from cosine squared to this expression of cosine of 2 times theta. So make sure you catch that when you're using it. So back to this problem I gave you. So we know we're supposed to use a power reduction formula. So we could take this cosine to the 4th. Well, what I know is something about cosine squared. But cosine to the 4th, I mean, you've seen this happen before, is cosine squared, so cosine of 5 theta squared, right, if it's 4th power, d theta. And so now if we apply power reduction, that's 1/2 1 plus cosine of double the angle. So if we're looking at 5 theta right now, this will be cosine of 10 theta. And close this parentheses, all of that squared. So I would square the 1/2 first. 1/2 squared, so that's 1/4. Integral of, and then this part squared. So the 1/2 squared is constant coefficient. I like to bump those out front and then forget about them for the time being. 1 plus cosine of 10 theta squared, so that's 1 plus cosine of 10 theta times itself. 1 plus cosine of 10 theta. So if you multiply that out, that's 1 times 1 plus cosine of 10 theta plus cosine of 10 theta. So plus 2 times cosine of 10 theta plus cosine of 10 theta times itself. So that's cosine squared 10 theta. d theta. At this point, you could start integrating. Because we could go ahead and integrate 1 by itself. With respect to theta, that's going to be theta. Plus 2 times, you could also go ahead and integrate cosine of 10 theta. I gave you a rule for that. The integral of cosine of kx is 1 over k times sine of kx. So in this case, that's 1 over 10 times sine of 10 theta. Okay. So we took antiderivative of this, we took the antiderivative of this. This, we can't do a straight antiderivative. In fact, in order to integrate this piece on the end, you're going to need power reduction again, unfortunately, because we find ourselves integrating just an even power of cosine. So we're stuck with just an even power of cosine. We're going to have to use power reduction again. So this cosine squared of 10 theta will get replaced with 1/2 1 plus cosine of double the angle. If we're going to apply power reduction again, we have to double the angle again. So cosine of 20 theta. So that's going to get replaced there. But I'm going to erase the board here and write it up at the top. Oops, I almost erased the replacement there. Okay, and be careful. So we still got this 1/4 out front. I'm going to leave it out front still for now. So theta plus the 2 over 10 here I can reduce to 1 over 5 sine of 10 theta. Okay, and then we're integrating 1/2 1 plus cosine of 20 theta d theta. Okay. So the antiderivative here, we could bump the 1/2 outside. The antiderivative of 1 with respect to theta is just theta. Antiderivative of cosine of 20 theta, so that's that old integral of cosine of kx, is 1 over k. So 1 over 20 sine of kx. So in this case, sine of 20 theta. Okay, and so now we've evaluated that integral there, plus c. We've still got all this other stuff in front. I guess I'll copy it down. Theta plus 1/5 sine of 10 theta plus that. Okay, so everything's integrated. We should clean this up a little bit. So first of all, you can combine, you have 1 theta here plus 1/2 theta here. So think of that as 2 over 2 plus 1 over 2. So this is 3/2 theta when you combine this with this. And then 1/5 sine of 10 theta. Don't forget to distribute this 1/2. So the 1/2 theta we've already combined over here. 1 over 2 times 1 over 20, so plus 1 over 40 sine of 20 theta plus c. And then so for the final answer, we could distribute the 1/4. I think, you know how to distribute 1/4. So I'm going to box this up here. And there you go. So because we had to use power reduction twice in this example, it ended up a little long. But this is overall how you deal with integrating even powers of sine and or cosine. So remember, if you have an odd exponent, your life's a little easier. Just break off one power, call that du, figure out how to write whatever's left in terms of u. If you have only even powers, then you're going to have to use this power reduction formula in order to integrate.